So we learned about the Doppler effect. I want to solve a few more problems. So our equation was our new frequency that we hear is equal to the speed of the wave plus your speed if you're moving toward it divided by the speed of the wave minus the speed of the source, and these two numbers are positive if they're moving toward each other. Question: how would you solve for C?
C divided by C is 1.
That's not how you do algebra. How do you solve algebraically for the... Yeah. So, for example, 1 plus 1 divided by 1 minus 2. So you're saying when the 1 divided by 1...
Multiply by 1.
Multiplying by 1 does nothing.
Multiply by C.
No. Come on, how do you do algebra? This C minus Vs is the entire denominator. You can't break it up. You can't break up the denominator. You have to treat it the same thing. You would multiply by the denominator on both sides. So this becomes C minus Vs over here. And when you multiply on this side, it cancels out, leaving you with C plus VR F naught like that. So basically, F equals C plus VR divided by C minus Vs times F naught. I'm just multiplying by C minus Vs on both sides. Anything divided by itself will cancel it out. And I'm left with this. Now we need to get all the C's on one side. So I'm going to FOIL this out. C times F. And C times Vs. And F times Vs. Likewise over here. C times F naught plus F naught times VR. And now I'm going to move all the C's to the left and everything else to the other side. So moving this over here, I get CF minus CF naught. Moving this to the right side, I get VSF. It becomes positive over here because this is a subtraction. If I'm adding to both sides, it cancels it out over here. And this has a common factor of C, so you can factor C out. Like that. And then I can, because again, if you were doing reverse, C times F is CF. C times F naught is CF naught, and there was a minus in it. And now that we have something multiplied by C, we can simply divide both sides by that something to get C by itself. So Vs times F plus VR F naught over F minus F naught. That is how you solve for C. It appears twice. You have to collect it to get it. Some of the homework problems do require you to do algebra like this. I think I've changed the numbering on the homework. Yeah, it's number 8. Number 8 is the hardest problem on it. It requires a lot of algebra. Because basically it tells you you're moving at some velocity to the right. There's a mountain. And when you get past it, it tells you a new frequency. What this basically tells you is you're going to have two equations. You're going to have an equation for when you're moving toward the mountain. because your speed is going to be positive, and because you're moving toward the source. And when you get away from it, it's going to be negative. And basically, you're going to have two equations and manipulate them together to get the value of c. So you need good algebra skills for that problem. And there's only like 12 problems in the homework, so they're kind of weighted very heavily. So make sure you do them. But today, we're going to look at Snell's law and the law of reflection. Let's do the law of reflection first. It is one of the most complicated laws in physics that we'll learn. Let me do attendance. So, the law of reflection deals with mirrors and reflections. When a laser or any light strikes a surface, one of a few things can happen. One, it can be absorbed. The energy of the light will be absorbed into the material, causing it to get hotter. Another thing it can do is it can go straight through that surface. That'd be like glass. Or it can reflect off of it. So imagine we have a mirror, also known as the plane of reflection. What do we call a perpendicular line? What's another name for perpendicular? So I'll give you a hint. The name for parallel is tangent. If you have another line coming and barely touching it, it's called normal. The normal line, normal is perpendicular. So this is the normal line. If we have an incident that hits the surface right at the normal line, so this is the incident ray, we always measure the angle off of this normal line. This normal line is imaginary, so this would be the angle of incidence. Then it's going to reflect off of the mirror, our plane of reflection, at some other angle, theta r. This would be the angle of reflection. This would be the reflected ray. How do you think these two angles relate? It's very complicated. They would be the same. The law of reflection is simply theta I is equal to theta r. The most complicated equation we'll ever use. They're the same angle. Do you have a full body mirror?
No.
Nicole, do you have a full body mirror?
Yes.
Why?
Because
why?
for me to look at the full outfit.
But why do you... What?
She needs to look at
But-
she go shopping.
But why?
What do you mean, why?
So let's say that we have a mirror that is exactly half your height. So 1/2 your body height. And So it's 1/2. So if you look at the very bottom of this mirror, angle of reflection tells us the light coming off your feet will hit at the bottom and bounce up into your eyes. You only need a mirror half your body height to see your entire body.
Okay.
Again, in order to see your whole body, you only need a mirror half your body height. Anything bigger is, well, waste of money. It looks nice, but if you'll notice when you're looking at it, all this bottom portion of a full body mirror is floor.
Yeah, I like my full body.
You'll notice that at how I've drawn it, these angles are the same. So light that reflects off your foot hitting at the bottom will reflect up. Light that, and again, it would be situated like this. So to look at light coming off the top of your head, it's going to bounce like right here. You really don't need it. You need it like right here. I've drawn it wrong. Because light coming off the top of your head hits the top and then bounces back like that. And you'll notice that normal line, these are the same angles. There's a little fun fact about mirrors. Law of reflection is very easy. This is supposed to say reflected. Right. But law of reflection is just a useful thing. You don't really, I'm not going to really do much with it other than a few problems. You just need to know that if it is reflected, it'll reflect at the same angle. So if we have, for example, a mirror and it hits at an angle 20 degrees here, first you should remember that you should measure it off of this angle, the normal angle, which, what is this angle? 70 degrees. It is going to reflect at 70 degrees here or 20 degrees here. It's the only thing you need to know about law of reflection. If you do it almost vertical, in other direction, so 20 degrees here, it's going to bounce back up at 20 degrees here. Just pay attention to the wording. If it says just an angle, assume all angles are measured off the normal line. If I say that it bounces at an angle of 20 degrees, you assume it's done from the normal line. But if I say measured from the plane of reflection, it'd be this angle. So you need to convert it into that. Or if I ask what would be the angle that is reflected in reference to the horizontal. This is from the horizontal, and the vertical is called your normal. But we're going to be looking at Snell's law. Suppose we had a boundary where on this side is air and this side is water. And we had a beam. Let's draw my normal line. coming down like this at some angle theta. So this is the angle of incidence. This is your incident ray. So incoming, incident means incoming. One of the few things could happen. Remember, it could either be absorbed by the water. It could be reflected off. We know the angle of reflection. So it could be, in real life, some light is always reflected off. What's another thing that could happen? It could be reflected, it could be absorbed, and go through. But what angle will it go through at? So this is also known as the law of refraction. So this is the refracted ray. Theta r. You'll notice how I've drawn it. These two angles are not the same. So whenever you go from one material to another, the speed of light, the speed of a wave actually changes. Light actually slows down when it enters different materials. The equation for this is N1 sine theta 1 is equal to N2 sine theta 2. Angles are always measured from the normal line. And N is called the index of refraction, I think. Let me make sure. Yeah, N is the index of refraction. And this line can be also called the interface. There's an interface is the N, index of refraction, is equal to the speed of light divided by the new velocity. So speed of light in a vacuum speed of light in medium, and this is refractive index, also called the index of refraction or refraction index. I call it both the refractive index or the index of refraction. So, for a vacuum, N would be, well, the speed of light in the medium. There's no medium, it's just the speed of light, is 1. For air, N is ever so slightly different from 1. You can basically treat the speed of light in a vacuum and the speed of light in air as being the same. It doesn't slow down much in air. Let me find some current values. It's like 1.000293, which means you need at least 5 significant digits to do it. Water is 1.3 carried. Our N equals 1.333. Glass, it depends on what type of glass, but a good value that we'll use in this class is 1.5. Again, they vary, but it's roughly about that. So then, let's do air versus water. Again, you can treat air as being a vacuum itself. So we have a light coming in at 45 degrees. At what angle will it be reflected at? So it would be N of air times sine of 45 degrees has to equal N of water times the sine of theta in water. Divide both sides by N water. So N air divided by N water times sine of 45 degrees is equal to the sine of theta that we're trying to solve for. And to get rid of the sine of theta, we do inverse sine on both sides. The inverse sine of sine cancels each other out. And we get theta r. So your theta r would be equal to the inverse sine. N of air is 1. N of water is 1.33. Then times sine of 45 degrees. And make sure your calculator is indeed in radians. We get 32.0367 degrees. So when you go from low index to high index, you should know that the angle is going to bend toward the medium. This also can work in reverse. Let's say I had a flashlight here, and my flashlight was pointing at the exact same angle. It's going to be the exact same thing. It doesn't matter what direction the light's going in, it's going to work out the same. If I do it at roughly 32 degrees here, it's going to come out of the water at 45 degrees. Ever go spearfishing? So if you see a fish here, so you're sitting in a boat, and you see a fish that appears to be right here. So looking at a straight line, you assume it's a straight line toward it. Where's the fish actually? In front. Because you should know that the angle is going to, as we go from high index to low index, this angle right here should increase. And I've exaggerated it a lot. It wouldn't have been this much. But he's actually closer to you than he appears to be. This is why you see this. If you see a pencil in water, you'll notice that looking through the glass and water, that there's a disconnect right here. It's because light gets bent as it goes through. So looking into to the water, this is where it actually is, but this is where it appears to behave right here. And this is my favorite picture showing Snell's law. Physics is fun. An extreme example. It looks as if he's holding his own head. It's because even though he's really right here, his body appears shifted over. An interesting way to think about this to help you get some intuition for it. Light always takes the fastest path. It's as if the light tried every single possible way to get from point A to point B and just magically chose the path that took the least amount of time. This is actually one interpretation of it, that light tries every single possible way and it just happens to always choose quantum mechanical stuff. Let's get some intuition. Let's say that we have a really lot of mud right here. And then we have concrete here and concrete here. Obviously, and you're running, you're sprinting, and let's say this is very deep mud. Obviously, it'll be really slow for you to run through mud, right? So let's say that you are here, and you want to get here. If we were to draw a straight line, 2/3 of the time you're in mud running very slow. What could you do differently to speed up your entire journey? So you can go over here and then run like this. You can go to the midpoint, go over, and then go like that. Mathematically, if you look at it, it's more like this. You don't go exactly halfway, and you don't go purely horizontally. You go at some small angle. Mathematically, yes, you're spending more amount of time on in the mud than if you were to just go straight across it. But look at the total distance you traveled. This this one has least distance overall. Obviously, a straight line is the least distance. Um, uh, so a straight line is the least distance. But this one spends less time in the mud, but also reduces your overall distance. So going from low index, again, the angle would be very steep, to high index, we're going to bend toward this normal line. You might notice one other thing, because this surface and this surface has the exact same index of refraction. Look at the angles here. These two lines are parallel, which means if you had some glass, even if this becomes very steep, overall, the light and air will all still be parallel. You won't see any distortion through the glass. All the light that goes through it will appear normal on the other way away. It's just been ever so slightly shifted over. That's the reason why you can look out that window and everything appears normal out there. But in reality, everything has been ever so slightly shifted over. You won't notice it too much with these glass windows and everything like that. Also, if you're looking directly on through a mirror like this, there is no deflection. It goes straight through. It's only if you're looking at it at extreme distances or angles does it actually shift. So the more this angle changes right here, the more the shifting will become noticeable. Now, in the pencil case, you noticed a severe shift or distortion. So in his body appears normal. There is no distortion. But if I do pencil and glass, the pencil looks fatter. Why is that? It looks like this pencil is now twice the width of the original pencil. It's because the glass is curved. So, because of this, there's multiple different paths. So we have this line right here. What happens is, looking at your eye, is going to want to, I'm exaggerating. It's going to take different angles and spread out more because it's like that. Versus if it was like this, we'd see all the lines parallel, everything shift over the exact same amount. Because all these distances would be the same and so forth, we'd see the same level of thickness here. But because there's different paths throughout this, because this is curved, it changes its story. Think of a magnifying glass. A magnifying glass works on the same principle. If I have a single point here, and I touch this point here, or let me exaggerate like this. So I have a single point here. If I go right here, again, we have to draw the normal line, the perpendicular line. So the perpendicular line looks like this. And so I have an angle here, theta, this is going from air to glass. So I need this angle to be smaller. So it'll bend like this. And if I put it right here, the perpendicular line is straight, so it'll go straight through it. And then if I come over here and do this, the perpendicular line is now like this. So it needs to bend closer inward, like that. And we can now see that these objects will converge on a single point. That's why you can get a magnifying glass and have the sun come over here and get to a single point and concentrate all the light to a single point. Because the glass is curved, anywhere the light hits the surface, it's mainly the fact that this normal line is constantly changing. Whereas if you have a straight, obviously no matter where this point hits, the normal line is always going to be the same, parallel to each other. Right? It's always going to be vertical. But here, the normal line is always going to be changing wherever it hits. So here we have a concave mirror, or lens, and a convex lens. Parallel lights converge. So parallel lights from the sun will cause them to converge to a single point. Where a concave lens, parallel lights cause them to diverge. You might have also seen a prism. So I've been treating this as if it worked for all light. This number here is actually not constant. This is an approximated version of the refractive index. It actually depends on the wavelength and frequency of light. Here's an important thing to know. When light enters a medium, the frequency does not change. Which is so weird because they always do lasers and wavelength. The wavelength is going to change based on what medium it's in, but the frequency is a better unit. It's wavelength that changes. So you might have a really long wavelength coming in, and then it might increase like that, or decrease. The wavelength, the distance between them, will decrease. But the frequency has to be the same. If ever a crest is hitting this, let's say a crest is hitting it ever once per second, that means that when it eventually hits another surface, it still has to be at the rate of once per second. That's it for the day. We'll look at more examples tomorrow. And I'm testing on Thursday, so we won't have class Thursday. Try to have your homework done this week.
Oh,
Not the 6 weeks.
before baseball game was canceled, not.
If you have any questions, don't turn it in incomplete. Ask. I get here in the morning and stop by my classroom and ask. But you might have wondered what a rainbow is. Are planktoids covered with a prism? This actually depends on frequency of the light. So red light is not going to refract as much, whereas violet light will refract the most. And what this means as sunlight, which is white light, it's composed of all the colors, hits a droplet of water, the water is going to be almost a perfect sphere. We can calculate the angles that it reflects off of. So angle of reflection is going to be equal to angle of incidence is going to be equal to angle of reflection right here. So this is a reflected light. This is a refracted light. So we can go from air to water, reflection, then from water to air. You'll see violet has moved the most, red is the least. And this gives you the appearance of a rainbow. Shine white light through a prism. The red light won't move as much, and the violet light will move the most. And that's how you can separate white light into its various colors. Here you can see that there are two normals. So you should apply the law twice. This effect is on Pink Floyd's cover. So technically, whenever I say the index of reflection of water is 1.33, that's the average for visible light. You should technically do it for every single color. I don't even know where you'd look up those values for individual colors.